again, Colloquium. It is my great pleasure to welcome Professor Naomi Leonard, Edwin as Wilsey Professor of Mechanical and Aerospace Engineering, and also affiliated with the Applied and Computational Mathematics program at Princeton University. She is a MacArthur Fellow of the American Academy of Arts and Sciences, SIAM, IEEE, IFAC, and ASME. Her undergraduate degree was in mechanical engineering from Princeton, and the PhD was in electrical engineering from the University of Maryland. She is one of rare people who talk equally easily and productively with mathematicians, roboticists, and biologists. And whenever I have a pleasure to talk to her or to people in her group, and I had a pleasure of doing it a lot last year when I was on sabbatical, I always learn a lot. So I'm looking forward to learning a lot from this talk as well. Thank you so much.
But thank you for coming. It's great to be here. So I want to talk about a collaborative project to develop a nonlinear dynamical framework for model-based investigation of the mechanisms that explain social decision-making, collective behavior, including both agreement and disagreement, so maybe you think of it as consensus and polarization. And so I've been interested probably for a couple of decades now in collective animal behavior. So what is it that individuals do that lead to what we do at the level of the group, and how they manage sort of these incredible tensions. So for instance, one of the tensions I'm quite interested in these days is the tension between flexibility, responsiveness to changes in the environment, and robustness to false positives or to noise or to disturbance. So how is it that, I mean, I don't think, well, certainly I don't necessarily know as an engineer how to handle both of those all at once. How is it that these natural groups, like animal groups, but also collections of neurons working together in a network, and maybe people, I don't know how well we do, but manage to change when they need to and reject noise and disturbance. And so from my experience of working with biologists and working with social scientists and working with neuroscientists on particularized systems, I also work on engineered systems. So how do we design robotic systems to work as a collective, so as a group they do better and they can manage in environments that are complex. I've done a lot of work on robotic observation systems in the ocean. How do we sort of abstract out through mathematics a framework that allows us to query the evolved systems, to think about new ways to design, to learn from one particularized system about another, but through some kind of abstraction, so that we can get a handle in a maybe analytically tractable and generalizable way. So this is joint work. Anastasia Vizquerda is a third-year PhD student with me at Princeton. Alessio Franchi is a professor at UNAM in Mexico City, the math department, and Marty Golitsky is a professor of math at Ohio State. And so the big picture is we want somehow to develop, maybe in a systematic way, analytic models so that we can investigate the mechanisms that underlie social decision-making. We want a systematic approach to exploring the role of network structures, so who's interacting or communicating or sensing whom. And can we explore the role of individual differences? So what if not everybody does the same thing or has the same capabilities? And biases and uncertainty. So how can we handle, I mean, this is a lot. And how do we go about doing this in a way that maybe we can sort of step up the complexity, but maybe start at something that gives us some of the fundamentals. And, ideally, we'd like to come up with a framework that allows us to make testable hypotheses, and then also allows us to do design. So the starting point here is I want you to think about decision-making as a nonlinear process. So I want to think about states as opinions that live, that are real, valued, and change continuously in time. So it could be the state as the opinion of an agent about an option, and it changes over time, and it can change because of what it learns about its environment or what it learns about from its neighbors. And I want you to think about decision-making as the transitions among states, so like a transition from indecision to a decision, or a transition from a consensus decision to a polarized decision. And I want to understand the system as a nonlinear process where parameters or inputs can be representative of features of the agent, something about the option, something about the context of the network, etc. And so the natural language, if we're thinking about a nonlinear process, to describe transitions in states is bifurcation theory. So a bifurcation diagram, what does it do? It describes how a state transitions as a parameter, we call it a bifurcation parameter, varies. Right? So the bifurcation parameter, so for instance, here's a very basic, this is the Pitchfork Bifurcation. So on the vertical axis, this could be the decision of the group, positive if they're for option A, negative if they're for option B, and on the horizontal axis could be this bifurcation parameter. Maybe it's sort of how much attention, how strong is this sort of social effort parameter, how much am I paying attention to everybody else. And so here the solid lines are stable solutions. So for any fixed value of that social effort parameter, I see all the solutions and I see their stability. So if it's solid, it's stable. If it's dashed, it's unstable. So to the left of the origin, we just have a stable solution and indecision. Everybody is neutral. To the right, this indecision becomes unstable, and essentially the group seems like they're going to flip a coin because they have a stable solution for A, a stable solution for B, and maybe just whatever the initial conditions are will take you. So this is clearly in a very symmetric setting where there's no difference between the options, and choosing A or B doesn't really matter. So then you might say, well, that's very special, right? Everything's super symmetric, but before I get there, so the little arrows just sort of show you the way the system would flow for a fixed value of this parameter, but I don't want you to think of this as a very static kind of picture. I want you to think about the fact that if we were to dynamically change this social effort parameter, maybe even at a slower time scale, we would actually, a group would transition from indecision to making a decision. Okay? So this is sort of an overview of the whole story in a very symmetric case. And then, but what if we understand that there's going to be, well, there's always going to be some asymmetries or bias, or in our case, there could be all kinds of things that make this not perfectly symmetric. But bifurcation theory tells us what happens in that case too. So it tells us not only how to describe solutions as a function of a parameter, but it tells us what happens to that bifurcation diagram when you introduce some kind of perturbation or asymmetry. So that's the unfolding. So if there's some other parameters or inputs that are like a bias coming into play, so here now there's a bias. Maybe option A is better, or maybe there's enough individuals that have a prior preference for option A, and you can see that the bifurcation diagram looks a little bit different, but it looks the same when we're far away, right? So all this sort of sensitivity, we get some kind of sensitivity right near the singularity, which is the bifurcation point, right? And then we get a lot of robustness away from it, because things don't change. The overall picture doesn't change as we sort of zoom out, right? And we can think about, again, the same kind of story in the unfolded setting when the parameter changes in time. Right, so we already have sort of a notion of sensitivity and robustness. I told you that was kind of a tension that I'm really interested in, and I'm going to come back to that. But I want to motivate thinking about bifurcation diagrams and nonlinear processes as a way to understand behavior from two examples of collective animal behavior. So this is a sort of famous paper by Cousin et al. That appeared in Nature in 2005, where this was actually a simulation study, so they were simulating sort of planar particles, moving with these simple schooling-like rules, like you're repelled from somebody who's too close, you're attracted if they're too far, you're aligning. But here they had two equal-sized subgroups. One preferred to go in, say, direction 1, and another preferred to go in direction 2. So they were sort of balancing these social terms plus this kind of, hey, I think there's food over here, and these guys think there's food over here. And so what you're seeing here is the result of these many simulations where you're looking at where the group went as a function of the difference in the preferred direction. So let's say the subgroup 1 wants to go in the 0 direction, and then they vary from 0 to 180 degrees when the other group wants to go in 180 degrees. And they show you so the color, the heat map is telling you the probability that that's the direction they're going to go in. So you can see that there's sort of this critical value below which they can't really distinguish, and they average and they go down the middle, above which, with equal probability, they either go in the direction of subgroup 1 or subgroup 2. They don't split, so they go in one way or the other. And actually, sure enough, when they try different size groups, you see, okay, when there's more for direction 1, they go in direction 1. Although there's still some times when they take the other path. But this looks to me like a pitchfork bifurcation, doesn't it? And this looks to me like an unfolded pitchfork bifurcation, right? And we should expect that. I mean, there's a symmetry, and there's a decision-making problem. We should expect that there's some kind of parameter that should give us this, and if we break that symmetry, we should expect that we would get sort of this unfolded bifurcation. So here's another example that starts here at Cornell. So this is the work of Tom Seeley, who studied honeybee nest site selection. And in 2012, he and colleagues published this really beautiful paper in Science where, they had already known through the Wagglelands how the bees are able to select the best of N. They know what it means for a nice cavity in a tree to be, a 5-star hotel versus a really, roadside motel. But here they were asking this question: well, what if they're equal value? So symmetry again. So equal value nest sites. What do? Do they deliberate forever? Is it like Congress? Do they end up in a deadlock, or can they flip a coin? Because if they don't flip a coin, they are probably, that's really bad. They need to find a nest site. They're waiting there on the tree. So this is a mean field model that they wrote down in this paper in 2012. YA is the fraction of the population assumed to be very large. That's for A. YB is the fraction for B. YU are the uncommitted. So 1 minus YA minus YB. And so in this little picture, let's say the B is on the right and it has a value, VB, that's greater than VA. And so you see the different kinds of terms that come out of what they actually do. So the first term, well, let's look at the second term is commitment. Somebody, there's 10,000 bees, 300 or 400 go out, they scout out a site, they get committed, and so they make that the rate of commitment is proportional to the value of that site. If they keep going back after they do their waggle dance. So they do a waggle dance, which is advertising. That's this recruitment. So an uncommitted sees A doing a dance, and with the same proportional to the value of the site, they get recruited. But once you're committed, you go back and you actually lose interest if there's nobody there. And so that's the sort of inverse proportional to the value of this decay term. And then the last term is the stop signaling term, which is this kind of new behavior that they have discovered recently, which is it's sort of like a shut up signal. So one is dancing for site A, and the other, who's already committed to site B, will headbutt the other one, which sort of tempers the dance. And you can kind of intuitively think, yeah, that will allow them to maybe come to a decision a little bit faster, so they're not going to just dance forever. And sure enough, it turns out that sigma, the rate at which they're doing that, is pretty important for them to be able to flip a coin. So here's just an example of the simplex that describes the dynamics here. So the vertex B is when everybody's for option B, with vertex A is when everybody's for A, and vertex U is when everybody's uncommitted. And this is just sort of showing you what the flow looks like when B is better than A. Now, what if we look at the case when VA is equal to VB, which is equal to just some V, so equal value sites. So here's what the simplex looks like when there's only very little bit of this stop signaling. So sigma is small, and we have one single solution, that's that solid black circle, and it's perfectly at deadlock. Half are for A and half are for B. Okay, they can't flip a coin. And yet, if you crank up the stop signaling, you see, I mean, if this is our pitchfork bifurcation, that becomes an open circle, becomes unstable, and we have two symmetric solutions. One, everybody's for B, everybody's for A. Right? So if I draw the picture of this is sort of a projection of the solution. So up here at 1, everybody's for A, down here everybody's for B, here everybody's split. As a function of sigma, I can see that in this symmetric case, I actually get a pitchfork. It even gets more interesting because the bifurcation point is inversely proportional to the value. So if they've evolved to do stop signaling at a certain value, like right here, and the options are really poor, the pitchfork will be way over here, and I'll be stuck in a decision, meaning that they probably will wait for a better site to come along, whereas if the options are really good, the bifurcation point will be here, and then they'll quickly flip a coin, which is even crazy. I mean, even more amazing than one could even imagine. And sure enough, again, this is what we should expect, right? If one option is better than the other, we get the unfolding, exactly what we saw before. Yeah.
Sorry, the stop sign, sigma. So once the butt heads, they become undecided, both of them? Is that the logic?
No, it's just that they do this, the waggle dance. I mean, I don't really have time to explain it. I can tell you afterwards about it. But they, if they're more excited, they do more of the waggles, all this kind of thing. And so if somebody's headbutting you, you basically, it gets you to stop dancing. Somebody's like, please shut up, or so they stop dancing. And so we're looking at how to model how that leads to, what is the mechanism? How do we explain that as a mechanism for allowing them to flip a coin when they have this kind of situation? So here's a little bit more about this. So this is also motivating. So suppose I can't help but to think about this parameter as something that what if we could vary it? I don't know if the bees do, but what if we could ramp up stops it? Maybe they do. If they sit there forever and no third option comes, maybe they say, okay, fine, we've got to pick one, and then they ramp it up. So this is just take that model and ramp up sigma. It's exactly what I showed you in this little picture. I'm going to go past the bifurcation. So here's a little simulation where we put some noise in those rates, and so here is the frequency. This is sort of the same kind of projection. So this would be like for A here and for B here, and you can see at the beginning when sigma is less than that bifurcation point, they're undecided, and then for probably as a function of initial conditions, they end up choosing A. But this is sort of a model for what I want to now generalize to multiple agents, multiple options, and I want to do it in a way that we weren't able to do. I want to do it and ask questions like in the mean field model. I can ask questions about role of network structure, who was actually there to see the dance. I can ask questions about distribution of individual differences like biases, right? In the fish model, it's a simulation model, so I can't even, they can't even tell me what how to explain that bifurcation point because it depends on all the parameters they use in some way. And so here's the idea. The idea is, can we develop a framework, as I said, using nonlinear dynamics, assuming that all of this decision making is a nonlinear process. I want to think about n sub A agents and n sub O options. The starting point is this symmetric story like I showed you. That pitchfork on the right, on the left, you know, everything. So let's add the biases in later. So agents are going to be interchangeable, options are going to be interchangeable to start. Because this allows us to conclude that the dynamics have to be equivariant with respect to permutation. So you have to be able to not change the dynamics by if I permute the options or if I permute the agent. So I have this S and A cross S and O symmetry. Okay, so then there are two problems here that I'm going to try to tell you what we've done. And honestly, I've never talked about them all in once, and I hope I don't have too many slides. But the first one is sort of what we call model independent. Sort of the question is, can we, using equivariant bifurcation theory, identify as a function of number of agents and number of options all, and Marty makes me add the word likely because there can be some non-generic things. So all the generic things that can happen. So all the decision-making behaviors and the transitions among them. So literally, for us that translates into finding all the branches or all the likely branches, bifurcation branches, because those describe all the different kinds of things that can happen. So we're interested in, agreement and disagreement, and I'll show you that it turns out the only things that can happen are agreement solutions and disagreement solutions and transitions among them. And the second piece is, so that's very abstract because it depends on some assumptions about your model, but doesn't depend upon the details of the, in our case, ODEs. So the second problem, and this is, this is Anastasia's work, is how do we then derive like a set of decision-making dynamics, not just that give us some, like in the case of the honeybees, well, first of all, it's not agent-based, but it's all consensus, right? They don't disagree in the end. So how do we define dynamics that realize all of those likely things with a few parameters? So the idea is, if I want to come up with testable hypotheses, I want there to be the whole plethora of possibilities, and then I could run experiments to rule things out and get, thereby gain more evidence about what might really be happening. But I don't want to start with only half of the possibilities. I want to see if I can capture everything that could possibly happen. And so the equivariant bifurcation theory does give us some conditions that have to be satisfied, and then you have to be. So then the idea is, can we do this with a small number of parameters so that things are amenable to quantitative analysis, so that we can examine, the role of different kinds of parameters, including the asymmetric and biased case. Okay, so I'm going to first talk about problem one, and then I'm going to talk about problem two. So we have a brand new paper just posted on arXiv. If you're interested. But here the idea is we start by defining the state of agent I as a set of opinions about each one is sort of like voting among the options. And so xi, super I is the agent, j is the option, and we assume it lives on a simplex. So you have a unit of vote and you distribute it among all the options. So your opinion lies in this simplex. And so then we have basically a product of simplices that defines the state space for our decision-making network. And the neutral point, right, when your opinion about every option is equal would be 1 over number of options. So if I have 2 options, then half for this, half for the other. So this is just sort of an example of the way we think about it. So here's the neutral point. So this is just one agent simplex. In the case where it's neutral, here it's undecided between options 2 and 3. It's rejected option 1. Here it's decided, or it's committed to option 2. If we had 2 agents, now we can start talking about agreement. So here they agree on option 2, right? Here, they agree on rejecting option 1 and being undecided between 2 and 3. Here, they disagree in the sense that 1 is for for option 2 and one is for option 3. Here they disagree in a different way. This one is choosing option 2, this one is rejecting option 2.
But this is like simplex as opposed to Rn, as in somebody's, one person has a stronger opinion. This is more powerful,
Yeah,
something like that.
I mean, in a moment I'm gonna shift it and look at the linear space anyway. So actually all the analysis done on linear space, so I'm gonna subtract off the neutral point and you can scale it. And I'm gonna look at when your votes actually sum to 0, right? So yeah, so I'll get there. Okay, so we would have a nonlinear dynamical model. I'm calling the bifurcation some parameter lambda, and then the idea is I want to make sure that my assumption is that here is the action of the permutation of agents. There's the action of the permutation of options, and I want these dynamics to be equivariant with respect to both of these kinds of permutations. And note, of course, that the neutral point is unchanged by permutations, right? So we always have this as our solution. And so then we can write down, a little bit more carefully some conditions which are essentially making sure that this is invariant with respect to permutations of these different elements in the arguments. Right? And these are the conditions that then ultimately will allow us to derive equations, decision-making equations. So then sort of the technical work is using equivariant bifurcation theory, so particularly the drop the slide. So the first prediction that equivariant bifurcation, it's too bad, is...
There's a whiteboard behind you.
Oh, okay, yeah. So the first prediction that equivariant bifurcation theory makes is to tell you that where you'll have bifurcations is on these irreducible subspaces. So irreducible subspaces means that the only solution invariant to these permutations is the neutral solution. And so those two spaces, this is such an important slide. I just wonder if it's in a different place. Okay. So those two spaces are the space of agreement, right? So when everybody has the same, so when x1 is equal to x2, etc. Except we're doing this in, okay, we define the z's, z minus o. Let's see, z is x minus o. Okay, so I'm going to subtract off the neutral point here, right? So that now my states, these zi, j's, are going to sum to 0. And when all of my agents agree, when they're all equal, making equal choices, it's the agreement space, which is much smaller than the disagreement space. The disagreement space is when all of the z1 plus, so now this is the big vector. So this is, I'm just saying that your options, your votes over all your options sum to 0. That's just shifting from the simplex now. Now I'm saying that agreement is, these guys are all equal, right? And disagreement is when these guys sum to 0. So that's like if there's 2, I'm for A, you're for B, and 1 plus the other is equal to 0. And so in some sense, it's a deadlocked situation. the group is completely indecisive. So individuals aren't necessarily neutral, but the system is still one.
How is the neutral, how is that defined? O?
O is, I defined it, oh, it didn't drop that slide. That's the neutral here. It's when you distribute equal votes. And in the shifted system, I subtract it off, so then it's just zero. So zero when you is being neutral.
So based on this slide with the picture, could I ask a question about agreement and disagreement? Because it seems like you're shifted to a more restrictive definition. Here on the board, they have to have exactly the same opinion for the agreement. Whereas in your slide with the picture, they have to be in the same part of the triangle.
Right.
So you will be sticking to those invariant subspaces in your analysis?
Well, I mean, as things branch off, or as we add unfoldings, things will be close, not exactly, right? So you may be converging towards perfect consensus, but if you have noise or disturbance or things like that, things won't be exact. So that's why we like to think about it a little bit more broadly. But mathematically, yeah, I'm going to call it agreement subspace is this space, and the disagreement subspace is this space, which is higher dimensional. And so it turns out that so then the second piece of equivariant bifurcation theory is computing, all the kinds of solutions that can happen in the branches associated with them, and that is this process of computing isotropy or axial subgroups. And so from this story, we predict. So the second prediction is that so this is consensus or agreement. This is polarization or disagreement, and the second prediction is that there's only two kinds of ways that we get disagreement, and one is what we call uniform polarization, in which there are equal sized groups over the options. So like half the group is for A, half is for B, and moderate extremist is the other kind, right? And that's when you have a small group that's for one thing, and a large group that's not as extreme about the opposite opinion. And I think it's easiest again to see some pictures. And so this is the example of an arbitrary, I don't remember how many agents are here, and three options, okay? So here, so W1 is the agreement subspace, and W2 is the orthogonal complement, so everything else, that's the disagreement subspace. And so you can see that these are the different ways you can get agreement. So everybody here is for option 3, or everybody here rejects 3 and is undecided, right? And then this is just the neutral point, this picture. These two are these two different flavors of disagreement or polarization. So this is the one that we call uniform, when there's a group for each one, and this one is this extremist. So we have these small that are very, very much in favor of option 3, and this large group is less dramatic, but they do reject option 3. And then you have all the variations on the theme. Okay, and so then the third big prediction is that with a sort of well-defined modulation of parameters, in fact, I'm going to show you a little animation that Alessio made where he's changing a single parameter that sort of represents some kind of balance between like just a global parameter between how much agents cooperate versus how much they compete. We can actually explore all the possible ways that agents might behave in terms of decision making. So here's a little video. So they started out at one of these uniform disagreement solutions. They seem to be going towards neutral. Now they, but that's not where they started. It'll eventually start over. There we go. Okay. Okay, so here they start at uniform polarization. You're going to see all the different kinds of things happen. So now they move into this kind of moderate extremeness. These green guys are more extreme. See a few of them switching over. But not enough to get, to have them come to consensus, because then they move back to some kind of dynamic around this kind of uniform polarization. And then you already saw the end of the movie, because then they come close together. And then they end up making a choice for option 2.
How come they didn't go all the way to the corner in option 2?
Because I think he's actually plotting the z's, and he's just putting arbitrary scaling on this picture, basically. Okay. So that's a little bit of a synopsis. I apologize for the missing slide. But it gives you kind of a sense, right, that we can, in principle, understand all the things that can happen, but it feels kind of abstract, right? Because wouldn't it be nice if we could just actually write down some nonlinear dynamics that do this? And so that's what this sort of second project is all about, right? So here's this ZIJ that represents the opinion of agent I about option capital J. Remember, they sum to 0 over the options. So here are the dynamics, and I'm going to unpack it for you, right? But first thing to notice is, here's this vector field, and we subtract off the average over my options, right? So that kind of keeps us in a, so that the sum of the Zij dots equal to 0. So if it starts at sums to 0, it's going to stay summing to 0. And then we have these terms which I want. This is some kind of damping term. This is some kind of old, social term, but there's two things going on, which I'm going to unpack for you. And then this is a biased term. Okay? And so I have one of these terms for every option and for every agent for each of the options. So let's just simplify to tell the story. So let's assume there are just two options, option A and option B. And I'm going to reduce the dynamics even further. I'm going to let xi be a half of my opinion of A minus my opinion of B. But of course, my opinion of B is minus my opinion of A, because they sum to 0. So xi is just simply ZIA, right? Right. And I only need that because my opinion for B is just minus 1 times that. And so I have just an opinion for, one way to think about that is, so agent I, right, so this is for all my agents. Each agent has an opinion. It evolves over time. When it's positive, it's for A. When it's 0, I'm committed. When it's negative, it's for B. And it should have some dynamics that look like this. But maybe it can't, this assumes it can measure everybody. If it doesn't have access to information from everybody, then it would be just some of the other states of its neighbors. Okay, so let's even start simply. Let's just look at the simplest possible story. So here is just a self-excited agent. So it has this kind of damping term. So I want you to think of as, this sort of the strength of how much I'm going to do anything other than just sit and not make a decision, right? Sort of controlling all the other input to my decision. And so I'm going to think about U as always being positive. And so here S is some kind of sigmoidal function. So we're very much inspired by neuronal dynamics, which is sigmoids, and actually all over biology, actually all over physics, right, where the saturation functions show up, right? So it takes value from -1 to 1. And inside is, so I'm just taking a saturation function of my own state, right? So what happens here is when U is less than 1, the zero equilibrium is the only solution and it's stable. When U is greater than 1, I get this, it becomes unstable and I have 3 solutions, 2 of which are stable. I get this Pitchfork Bifurcation. So just a single individual can actually make a choice in this sort of self-excited way, by cranking up this game called U. Right? So now let's suppose there are 2 agents, agent 1 and agent 2, making a choice between option A and option B. And so, okay, I could even just have them uncoupled. I could use those equations, and I get each independently could, depending, if I crank up U, I could get all 4 possibilities, like this guy goes for A, this guy goes for A, or this guy goes for A, this guy goes for B, this one for B, this one for A, etc. Right? And that's even before I've introduced. I can already get agreement and disagreement even without introducing any communication. Okay, but of course we want to understand what happens when agent 1 has access to the opinion, or can observe or can measure or be communicated to, or somehow maybe physically sense the opinion of its neighbors, right? And so we add in, so here's that first term, here's that term that I had previously, but now I'm adding in a saturation function on C, which is just a scalar, lives in this space, and xj is this guy's neighbor, right? We only have two agents, or you could think of them as 2 subpopulations maybe. And then we have this second term. Okay, so this is actually, I'm going to show you, this specializes from those dynamics I showed you at the beginning for multiple agents and multiple options. This is how it specializes when you have 2 agents, 2 options. But I'm also going to show you that this gives you all the possible things that can happen. And I'll show you that in a second. Let me first tell you from here, again, U is this kind of social effort, or how much an agent values in social interactions. And C, I'm going to interpret it as whether an agent is predisposed to agree with its neighbors or disagree. So this is this term that balances sort of this cooperative or competitive kind of notion. And of course, again, I've already done it, but let's just define agreement as when x1 is equal to x2, they have the same opinion, and disagreement is when x1 is equal to minus x2. And that's the only case I have here with 2 agents. Okay. So what I'm going to show you, what you get from these equations, and I'll show you how I can justify that, is a Pitchfork explosion. And if we look at this picture, so I'm plotting x1 versus x2, and then into the page this parameter u. So you can see in this magenta, the handle of, okay, so now it's not just a pitchfork, it's like a broom, right? So I have all these bristles coming out. But the handle is still indecision, and when u is less than 1, it's stable, and after the bifurcation it becomes unstable. I just have a lot more going on. If you think about it, I have 2 kinds of symmetries. Before, when I showed you that simple one, I just had the symmetry in the options. But here, like this blue pitchfork is along the axis when x1 is equal to a, x2. This is the agreement. So this is like, in this case, I have I have a stable solution for agreement for A and for B, and the black ones are the disagreement axis, right, which is orthogonal. And this is like, this one is, agent 2 is for A, agent 1 for B, this one is agent 1 for A, agent 2 for B. And then I have some things in between that are unstable. And so if I took a slice at a fixed U of just the handle before the bifurcation, maybe you can kind of see this is the agreement axis, this is the disagreement axis, and I just have that stable solution here, right? But the way I can convince you or prove to you that I get all the possible things that can happen is that I can actually, or not me, Anastasia can show you that these equations map onto, or are equivalent to the normal form for the S2 cross S2 equivariant system. So, and to do that, what we do is rotate the coordinates. So to the average and the difference. So instead of x1 and x2, now we're looking at the agreement and the disagreement axes. And so you can show that our equations are locally equivalent to this, which is, if you look up in Bolyvitsky and Schaefer, this is the normal form for the S2 cross S2 equivariant dynamics, right? So here, so you notice a couple things. There's two parameters, an m and an n. These are called modal parameters, and lambda is the bifurcation diagram. So we have these modal parameters because there isn't just one bifurcation diagram. So for these S2 cross S2 equivariant dynamics, there are actually 4 distinct bifurcation topologically distinct bifurcation diagrams, and they're defined by different values of m and n. But what we can show is that this bifurcation parameter lambda is like our u minus 1. So here lambda equals 0 is the bifurcation, so u equal 1 is our bifurcation point. And these m and n modal parameters we can show can be expressed in terms of that second parameter c. So whereas they have a two-dimensional space, that defines all the things that can happen, we take a 1D path through that space, and here's what the picture looks like. So this is the m by n plane. Each of these quadrants, so this is m equal 1, this is n equal 1. Each of these quadrants defines a different bifurcation diagram. Okay, so for different parameter values, you get a different something happening. And this gray curve shows you as you increase c from minus 2.7 to 2.7, this is this one-dimensional path. So our model with only u and c essentially takes us continuously through all the things that can happen. It's kind of a weird winding path, but so let me just show you. For example, in this region 4, this corresponds to stable disagreement, and the pitchfork in the unstable direction is actually, in the agreement direction is unstable. And this is the one I showed you before when both agreement and disagreement are stable. This one, agreement is stable and disagreement is unstable, and here they're both unstable, and those sort of mixed modes become stable. Okay, so we can pass through all the possible situations in this continuous way. But let me just show you what a slice phase portrait looks like. Just for example, so here you can see the stable disagreement and unstable agreement. Here you can see, stable solutions, unstable solutions, right? So the closer I am to here, the more I am stable. The closer I am here, the more these would be larger, these would be smaller. Here's the stable solution, stable agreement, unstable disagreement, and here's that sort of mixed stabilities story. So what can we do? So here's just sort of a very, very simple idea. What if I start in this, I start my C, I want to think about it like that stop signaling now. So U could be that stop signaling rate, that was like the bifurcation, but I could also think about this other parameter, which is this sort of like how predisposed I am to cooperate or to compete. And that's what I'm going to change. So I'm going to fix U, and I'm going to slowly, first I'm going to hold C constant so that we see that the solution, so blue is agent 1 opinion, red is agent 2 opinion. Here this is 1, 0, minus 1. So the blue one equilibrates to going for A, the red one for B, and that makes sense because this is where disagreement was stable. So it's converging to that solution, and then we just ramp up, kind of like we did before in the honeybee setting, ramp up the C. So we pass right through this place where they're both stable and land where only the stable agreement is, only agreement was stable. And sure enough, you see, what's kind of interesting is that we're not imposing, we're not micromanaging which one they'll choose, sort of as a function of initial conditions. They chose to both go to A. Actually, let me show you, this is kind of interesting. So we did a realization of this with robots. So this is like one, I don't remember which one. This is maybe agent 1, this is agent 2. Now they're moving kind of in 1D, each of them. And so over here is choosing A, over there is choosing B. Okay? And here is sort of a parameter plane. Here's U. So below U equal 1 is indecision. Above U equal 1 is a decision. And here are those different possibilities as you move from stable disagreement. You pass through that both stable regime into stable agreement. And but what I'm showing you here, so these guys are actually measuring I mean, this could be temperature or pollution concentration, or it could literally be somebody like an operator sort of controlling what they want to happen without micromanaging who goes where. We have theater lights, so they have little sensors to measure. C is the range from blue to red, and U, they're measuring the strength of the signal. So they're measuring these changes in the environment, in the parameters. And down here, you're going to see how the bifurcation diagram. So first we start an indecision. They do a little dance when they're close to an equilibrium. They go around in circles. So now we just cranked up U. So now they made a decision, and they happen to make the decision for option A. And they're in the agreement regime. And now we've moved C to the regime where disagreement is stable. That was kind of interesting because there's noise in their measurements. They jumped over a saddle point. So I would have thought they would have gone to this solution, but they went to that solution. Gives you a sense of the kinds of things that can happen in this. Okay, so I'm running low on time. So let me just sort of summarize a couple of the additional things that we have done and that we can do. So one is, if we try to understand now what happens when there's bias. If I remember, I'm looking at xi is the difference between the z's, and b's were the biases, so the beta is the difference in the biases. Bi bar is kind of like in the honeybees. It's sort of the strength of how much I care about this solution. This is a movie that sort of shows you, like, as you change the bias, how these this pitchfork explosion evolves. So, for instance, it helps you understand that, like, if beta 2 has a large magnitude, x2 is really sure about choosing option B. But if beta 1 is tiny, so we're sort of preserving, like agent 1 is going to flip a coin, right? And agent 2 is sort of more decisive. So it might go to agreement about, option B, or it might go towards this guy, agent 1 picks option A, and agent 2 picks option B. So to understand how to make the system sort of tunably sensitive, so how do we design, or how do we understand how natural systems might be able to distinguish, or how do we understand when systems distinguish between something that's a real signal, like, should I be flipping a coin, or should that small beta be something that I should be paying attention to, and I should really be going in the right direction? We can think about how our parameters might actually not be fixed or not be changing in the open mode, but be changing in a feedback way, in what we call active control. So this is inspired absolutely by neuronal dynamics, and thinking about like Hodgkin-Huxley equations and the gains in front of the terms being low-pass filters of voltage, right? So that your slowly reacting to a bias that's pushing you in a certain way, and it's like a reinforcement of that, and you crank up the gain. And so you can make sensitivity to that average input value, or you can make sensitivity to these, your opinion, your relative opinions, and this is what this expression. So we sort of do a low pass filter of these variables, and then we design a sigmoidal function so that we have active control over these gains. Okay, so I can't really tell you all about it, but the idea is that it can distinguish between small differences and large input differences. It can distinguish between small magnitude and large magnitude. So here it flips a coin, here it doesn't, because its signals are stronger than these signals. We can also do this with C, right? That was making a decision, and then we can also do it. So here the idea is you can sort of reinforce that there's disagreement and drive C like away from the place where disagreement and agreement are both stable into a regime where the one that should be emphasized is emphasized. So you're just making a system more robust because now you no longer have stability of the other option. And there's even more that we can do. We have a way of symmetric unfolding that splits these, so you can kind of like push all the stuff you don't want to have to deal with away, and you get even further robustness. And then the other story that I will just briefly summarize is, I sort of motivated at the beginning that I wanted to understand the role of network structure and the role of sort of distribution of other features of agents. And so we've actually done this, and this is a paper that was published in 2018 in the IEEE Transactions on Control of Network Systems. And so we looked at that in the case where we dropped that second term here. So really what we were doing, we were specializing for an arbitrary number of agents and two options to the case when we kind of got rid of the polarization and disagreement possibilities. So we're sort of specializing to consensus decision making, but now we've added in the fact that you might only be able to pay attention to neighbors as defined by some kind of network graph. I won't go through the story, but the summary is that, again, in the symmetric case, so now it's just a single pitchfork because we only have two options. We're enforcing, it's like the whole group is going to agree. We don't have the disagreement story. So we can prove that these dynamics give you consensus up. So on the consensus space, so the sort of at the singularity, the eigenspace is consensus. It is this where xi is equal to xj, etc. And you get the pitchfork there, and then you get the unfolding when you have some bias. And we can even say things like this is the G is the plot of the unfolded bifurcation when individuals have different betas. And we can even say that the contribution of an agent to how the group decides whether it goes for A or B is a function of the product of its bias times its eigenvector centrality. So for instance, these are just a few little pictures. Here's a network. Everybody, nobody is biased. We get the pitchfork. Now we introduce 4 that are for A and 3 that are for B. You can see the solution unfolds towards A. In this case, we have the same setting, but we changed up the network. So we changed. So now we have eigenvector centrality, so that the 4 that are for A are less influential than the 3 that are for B. And now the solution. And this is what we can predict. The decision, the consensus decision, goes for the other option as a function of, who has which bias and where they are in the network. And other kinds of things like think about the role of the strength of this, how much I care about one option versus the other. This is an example where we call it going from soft decision making to subcritical pitchfork. So it's a switch, right? You jump as you increase you go from indecision very quickly to a decision. Okay, sorry for running a little late, but So I guess big picture is, we developed this methodology to derive general equations that capture everything that can happen. We've started in on understanding things like role of network structure, distribution of bias, agreement and disagreement, how we get tunable sensitivity. We want to do this in the higher dimensional systems. What happens if these aren't global signals? What if individuals have, there's a distribution of parameters like the U's and the I's. How do we handle that? We have some interesting other theoretical results, like there's a prediction about whenever, the idea of what happens when you go from like choosing between 2 options to 3 options. We can say that some very interesting things happen. For example, all solutions, all these transitions are going to be those kind of switchy ones for 3 or more options. So, if you're thinking about voting between 2 parties, you're forgetting the fact that there's actually maybe the other options or third candidates. It's possible that putting in the third option might lead to some new insights. And then we're working with different kinds of collaborators to use this to understand social decision-making in animal groups and human decision-making. Also things with a colleague in cognitive control about how we, single decision-maker, but with different kinds of control inputs, makes decisions in multitasking, but I'll stop there. Thank you for your time.